really do fluctuate consequences.
Yeah, a little bit.
Okay, can everyone, is this too loud? No? Okay, great. So today, Max and I are going to be doing a lecture. Dr. Graham's in Prague at a conference and did not want to teleconference in. So we're going to do a few housekeeping announcements. There's been a lot of confusion and a lot of questions on the homeworks, and part of that's our fault for not making it very clear. So the DDR robot homework is currently out and released, and it's due on Monday, so that's March 4th, and it's going to be due at 10 p.m. like all the other homeworks. We're also releasing a homework, potentially later tonight, definitely by tomorrow evening, called Cryptorhythms. That homework is going to be due next Thursday, so that's going to be March 7th, same time at 10 p.m. And you'll have plenty of time to work on that and plenty of dedicated office hours. Also today, we're holding extra office hours from 4 to 6 p.m. in Rice 504. Those are just because we wanted to, because this homework was pushed back, because of some of the issues with the autograder, we wanted to have extra office hours for all of you. So those will be from 4 to 6 p.m. in addition to our regular office hours. So any questions on the announcements? Yeah.
Is the Cryptorhythms assignment also a programming assignment?
Yeah, it'll be a programming assignment. We'll release it as soon as we finish writing the test cases. Any questions on the exam? I know the exam just happened, and I'm sure you have some questions about that. Anything you want to ask right now?
Yeah, when are we getting that roughly?
So we'll be grading them next week when Dr. Graham gets back, and we'll turn it around as fast as we can. Yeah, so I don't want to go into details about autograder. It's kind of technical and might be boring. But basically, there was some code that kind of got caught in a really bad loop. And so they basically figured out what was happening and were able to fix it. So we gave you guys that extra time to submit.
So when are you going to have the exam graded?
So we can't make any guarantees, but we're grading it next week when Dr. Graham gets back. And we'll try to get back to you by spring break. And we'll have a regrade period for that as well. Anything else on the exam? Anything else in homeworks in general? Okay, we'll get into the content of the lecture. So today, Max and I will be discussing backtracking. Backtracking is a method of solving problems that's really useful in computer science and quite intuitive. So for a roadmap, we're going to start out with discussing Sudoku. So there's a warm-up exercise we're going to have you guys go through. Just raise your hand if you know a Sudoku card. All right, Max, do you want to?
Yeah, feel free to share with your neighbor. So I don't know if I have enough left, but I'll try to hand them out if I can.
So yeah, we're going to walk through Sudoku, what the problem is, the naive solution to it, and then the backtracking optimization. After Sudoku, Max is going to walk through something called satisfiability, and we're going to discuss how backtracking relates to satisfiability. So while Max is handing out the cards, we'll talk about Sudoku. So the rules of Sudoku are, there are 9 blocks, and these 9 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9. And each square can only contain the numbers 1 through 9 at most once, and at least once. And each row and each column can only contain the numbers 1 through 9 once. So any questions on the rules of Sudoku? Okay, we're going to give you guys 3 minutes to practice solving a Sudoku problem on your own. On the handout, we're not going to grade you. It's for your own edification.
Yeah, if you're a Sudoku wizard and have already solved this, explain how you solved it to your neighbor. Just, talk about Sudoku. So, go.
What? I think I might have once to do that.
I would just like guess.
The greedy algorithm is defined as design either a row or a diagonal or a column. It has both things filled out. So every row needs to have 1 through 9 exactly once. Every column 1 through 9 exactly once. Every 3 by 3 square needs to have 1 through 9 exactly once.
Right.
So sort of the greedy algorithm to do it is define a column or a row or a diagonal that has both things and use that. Like in the top, there's only 4 guesses we have to make. Right, so we know that what are the missing ones? 2, 4, 6, 9. Have to be in one of those 4. So there's only 4 possibilities. Whereas like the top left square,
Right.
we don't know anything. So we would probably try to solve either the top right square or the bottom left square first. Where do we go from there? You know that.
Oh, I looked up. Because I wrote one of the 2
Right, so like in the top right group of 3, you know that you need a 6 and 4, and they can't be in the left column because there's already 6 and 4 in that column. So those 2 top right squares, one of them's a 6 and one of them's a 4. We don't know which yet, so that's not a possibility. And for the same token, you know the top right one is not the 9.
I think it's on that side. Yeah. Oh, yeah, actually, right here, Max.
Or you just start doing, picking one possibility, and keep going until you find an error.
Yeah, I think that's using backtracking. Yeah. Takes so like it's a good gray, but it's not the most treatable.
We're not getting great.
You get an idea of the math test, you're smarter than I am. Maybe.
Okay, that was 3 minutes. Sorry to cut you guys off. We'll go over the solution in a second. Just first a question. Do you guys want these lights dimmed more, or can you all see the board? Is that better? Alright. No one's gonna fall asleep on me? Okay. Alright. So, here's the solution to Sudoku. Obviously you guys had only a few minutes to solve it, so you may have not gotten every single row and column. But just to highlight one particular box, we'll talk about this bottom left box. And so, as you'll see, we only have 1, 2, 3, 4, 5, 6, 7, 8, 9. So each number 1 through 9 appears in the box once. And also, let's take this edge column. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, all appearing once. And the same thing for this bottom row. So this solution observes the rules of Sudoku. And we just want to do the warm-up because we're talking about backtracking in the context of Sudoku for the first half of this lecture. So when we're thinking about Sudoku and the problem, there's this really basic brute force naive approach. And that approach is to generate every single possible solution. So if you consider your first empty square, so if we go back to the initial problem, if we consider this empty square right here, and let's say it can be 1, 2, 3, 4, 5, 6, 7, 8, or 9. And then we consider this square next to it. And we say that square can be any number 1 through 9. And do that for every single square. we'll generate this graph structure that we can think about it in this method, where we generate 1 through 9, and we repeat it for every single open spot on the Sudoku board. And for illustration purposes, I only drew one node branching out, but if you were to actually draw this graph out, every single node would branch out to its own subset of numbers 1 through 9. And with this approach, we're generating every single possible combination of numbers that we can fill in the blanks on the Sudoku board with. So any questions about what we're doing with this graph and how we're generating these numbers? Okay. So once we have the set of solutions, for every single solution in the set of solutions, if that solution satisfies the rules of Sudoku, add that particular solution S to C, where C is our final set of answers. So with this solution method, we will be generating some solutions that don't solve the puzzle correctly. And an important step for us is to make sure we don't save those solutions when we return our final answer. And so this method will only return the solutions that observe the rules of Sudoku. Some things to notice about this: the size of this graph is huge. It's 10 numbers to the n, where n is the number of nodes on the board. So for each one of these numbers, we go down n levels, where n is blank letters, where n is the blank boxes, and each level from each individual number is going to have 10 possibilities. Does that make sense? Any questions on this really basic approach to Sudoku, where we brute force every single possible solution and then check to see if they're valid? Okay. So this is a little bit inefficient, as you probably noticed. This is probably not the approach you took to solving it on your own. One such inefficiency is that there are some scenarios where we know a certain number is not going to work. So for example, this is just the top row of your Sudoku puzzle, and you're given 7 when you get the puzzle initially. Now we know that not a single one of these boxes can have the number 7 because it's already inside of that row. So out of the bat, we know that for all of these boxes that are initially blank, they can only be the numbers 1 through 9, excluding 7. This same process occurs in the columns, where we're given 1, 9, and 6 ahead of time. And we know that all of these blank boxes cannot be the number 1, 9, or 6. Rather, they can be any number 1 through 9, excluding those numbers. Any questions on this inefficiency, or questions about why it's inefficient? Okay. So there's this optimization that kind of becomes obvious, where we only recurse on valid branches. So when we're writing our solution, when we're creating our graph, if we go back to our initial problem, for this particular box here, we know that it can't be 1, 6, or 9, and we know it can't be 7, because 6 is right here inside of its subblock, and 1, 6, and 9 are inside of its column, and 7 is inside of its row. So we know that we should only recurse on certain solutions. So when we generate this graph, instead of considering every single number as a possible solution, we only consider numbers that are valid when building out a solution. And this allows us to make sure when we're generating this giant tree of solutions that we only build out valid branches that could possibly lead to correct solutions. So we'll walk through one more example. So in this example, we're considering the block highlighted in orange. And for each, just to remind us of the rules, each block can contain the numbers once, each row can contain them once, and each column can contain them once. So we know from the block rule that it cannot be 6, because 6 is already inside of its block. We know from the row rule that it cannot be 1, 3, 4, 5, or 6. And we know from the column rule that it can't be 1, 6, or 9. So based on all of these constraints, when we're considering our set of solutions, we know that that particular block can only be the numbers 2, 7, or 8. Now this notion is really powerful. It allows us to solve the problem much more quickly. So now we're going to examine some code that implements this solution. So this code solves Sudoku board, or solves Sudoku, takes one argument, and that's the board. And the board is just a matrix that contains the rows and columns and blocks. It's just an easy data structure to help you reason about the Sudoku board when you're writing a program. All it does is go through the board, and if the value in the board is not a period, where a period represents a blank, we populate the row and column and block sets. So that way we add that value. The next code chunk we implement is possible numbers, where we pass in these sets that we just created earlier. So for our solution, for every single possible number, 1 through 10, exclusive on 10, so really 1 through 9, we say if that number appears in any of the sets, and if that string is already inside of S, then we know to break out. Any questions on what this code is doing and how it generates the possible numbers for us? Okay. And this other code check will appear more useful in the next slide. But basically, given I and j, where I and j represent a position on the board, it grabs the next block for us. And this is the code where the meat of the problem solving occurs. So I've highlighted some sections that we're going to walk through right now that kind of implement this optimization we just discussed. So our first scenario is our base case at the top. If I is greater than 9 or if j is greater than 9, that means we've gone off the board. We've gone past the bounds, which means we've found a number to solve every possible spot in that given row column combination. So we know at that point that we can just return true because we solved that particular part of the puzzle. We also have this block of code that comes after it where we grab the next element, and if that element is not null, we skip it because we know it's already been populated. So we search on the next element. But if that element is not null, or sorry, if that element is a null element with a period, if it's a blank that we can populate, we enter our for loop. Now what this for loop does is it iterates through the possible numbers. Now, just to refresh your memory, we wrote this subfunction, possible numbers, that we defined in the previous slide that will tell us what is legally allowed to be in that blank given the current state of the Sudoku board. So for every number of the possible numbers, we set the board to that number. So we add it to our row sets, to our column sets, to our block set, and to our board in general. Then we search on the next element. If we can keep doing that recursively over and over and over again until we hit this eventual base case, then we know we just found a valid solution. So we return true. However, if that recursion fails, and if it ends up returning false, then this Boolean expression, if search, will value to false, and we'll move on to the next set of code. And at this point, we've tried a possible solution, and we've discovered that we cannot reach an eventual solution from that particular branch. So we just get rid of that branch, and we reset our board. This step's very important because if we do not reset the board, then we'll be we'll be iterating in our for loop over a broken board. Any questions on what this code is doing? On an exam, if I asked you to write all this code, you could write it all out? Okay. Hopefully we'll get you there by the end of the lecture. Any questions on this? Yeah.
How do you so if the solution is not valid, you're starting over from nothing?
So we're not quite starting over from nothing.
Are you going back to the previous the lowest spot where you can have another valid solution?
Yes, exactly. So if you'll notice here, when we're trying a value, we add it to our row set, column set, block set, and board. And if that value ends up failing this particular if statement test, and we don't return true, then we remove it from our row set, column set, block set, and we remove it from the board. So essentially, we revert to the state of the board before having considered that solution and iterate to the next possible number.
Can you explain the base case again?
So the base case is saying I and j represent columns and rows and columns of the board. So the top left corner of a Sudoku board is the 0th spot, and the bottom right spot is the 9th spot. And if in our iteration of elements, if we grab next, that means we've satisfied this blank, and we're moving on to the next blank. And if we have done that and we grab next and we reach off the board, that means that we've satisfied everything in that row, or we've satisfied everything in that column, which means we should return true, because that led to a valid branch of the tree. Does that make sense?
Yeah.
Yeah.
How is this not brute force if you're going all the way up to 9? On both of the squares?
On both of the squares.
I mean, if you're iterating to both ends, wouldn't you be trying every single?
So in Sudoku, we have to populate every single square to get a valid solution, which is why we go to the 9th of each row and column. However, in this for loop, we're not considering 1 through 9 for every single square. We're only considering what the possible numbers are for that square. And if we find a possible solution, when we recurse into that spot, the board isn't updated, and so for that version of the board, we assume that solution. Does that make sense, or do I need to re-explain that again?
That makes sense.
Okay. This is a pretty complicated concept to grasp initially. So, yeah.
So in Sudoku, sometimes you narrow it down to 2 different numbers that could be in the blank, and then in this solution, for example, you put in one of those numbers and keep on moving on. Then what happens if it fails later on? With that case near the end, remove it, then start back from that.
Exactly. So let's say for the top left block in your Sudoku puzzle, I put in 9, and we know 9 doesn't work. So what'll happen is we'll pick 8, so that way we're not at the end of the possible numbers. So all we identify is 8 and 9 as possible candidates for the top left spot. So we try 8 by first populating our row set, column set, and block set with 8, and also the board itself. Then we say, okay, this is a possible solution. Let's recurse and call this method on this new board we created. And this new board will make it seem as though 8 is given to us. 8 is a given solution to us. And once we have 8 as a solution, we can try possible rows and columns for other spots on the board. And we consider the next element in that recursion. And if that ends up returning false here at the bottom, then we know that this condition, search, will not be true, so we will never hit our return true statement. We'll reset the board, and then we'll continue. Any other questions? Yeah.
How do you check if the board is incorrect? Is it just if there's no possible numbers in the?
Oh, so you're saying what if the entire board is not solvable?
Right.
So what will happen is search will never return true, because we'll never have a valid set of possible numbers for a given spot. So we'll end up returning false in this function. It's a great question. Okay, so now that we kind of have walked through how Sudoku works, we're going to take some key takeaways from this. So one optimization we implemented for solving Sudoku is we use a data structure in the form of sets and in the form of an n by n matrix that allowed us to reason through the problem easily in our code and speed up the process of identifying possible numbers. We also reset the data structure every time the solution failed. So if a candidate solution did not work, we restored the board to its prior state. We also return all the way up the stack of recursions true if something is possible, and if it's a real solution to the problem. We ensure that we have a base case because the base case allows us to know when to stop recursing. We also made sure we had an invalid backtracking return case. And that invalid backtracking return case was this case right here on the bottom where after we reset the board, we returned false and moved on, returned false after the for loop, and moved on to the next part of the for loop. And we also used helper methods to make this a lot easier. When implementing backtracking, trying to write all the code in one chunk can make your life pretty miserable. So using these helper methods helped us write a cleaner solution to this problem. Any questions on these takeaways? Anything that's not clear about them? Or any way I should re-explain them? Okay. With that, we're going to formally define backtracking. So backtracking is when you incrementally build candidate solutions. And you abandon a candidate or backtrack as soon as you determine that that candidate cannot possibly complete a valid solution. So for Sudoku, let's map the Sudoku problem to this definition. So we are incrementally building solutions. We're trying each possible candidate. And if that candidate leads to a situation where we can solve the puzzle, we recurse down. If it doesn't, if every possible number for that candidate does not work, then we return false. And we abandon the solution. Now, some of you might be thinking about the geometric search problem from bird scooters and thinking, oh, that was my first version of backtracking. But there were some issues with that solution that distinguish it from a backtracking solution. And specifically, the first problem is we have the entire KD tree ahead of time. And in that problem, you were determining the closest point. So you weren't building any solution. Rather, you were eliminating possibilities. And one similarity is you did abandon bad solutions in the form of pruning. So you did have this property of abandoning bad solutions. However, you were not incrementally building a solution. So geometric search is not quite a backtracking problem. So any questions on the basic premise of backtracking or how backtracking applies to Sudoku? All right, so with that, I'll hand it over to Max.
Okay, does that sound good? Not too loud? Okay, so we just saw Sudoku. Sudoku is a classic example of backtracking, but the algorithm technique is applicable in all sorts of other problems. And one of those problems I'm going to talk about is satisfiability. Who here has heard of satisfiability? Okay, handful of people. This is a really important problem in theory, that is in like the theory of computation. So if you take that class, you probably have heard of it. But we're going to talk about it today in a more down-to-earth sense. How would you actually solve this problem? So let's look at the problem first. Here's the statement. Given a Boolean function with some Boolean inputs, Boolean function here means that it's Boolean valued, as in function outputs Booleans. Determine inputs that make this function true. That's it, that's the whole problem. It's a really easy problem to say, but man, is it hard to solve. So here's an example. Here's a function Can anybody just shout out, raise their hand? What are the inputs that make this function true?
1 and 0.
1 and 0. Yep. Or I'm going to use in these slides true and false, t and f. So here we say if we let x be t, we let y be false, f, and we plug those things into the function, it evaluates to true, because true and not false is true. So this function is satisfiable. Alright, how about this one? Take a moment, talk with your neighbor if you want, and try to find inputs that satisfy this function. Go.
Actually, yeah, it's artificial.
X not Y Z.
Does anybody have a solution? Raise your hand if you have a solution. Okay, yep.
Z is false, X is false, and Y is true.
Z is false, X is false, and Y is true. That wasn't the order I put them down in, but I think that's the same solution. That's what I got. No, you said 2 falses. Well, I guess this is satisfiable in 2 ways. I don't know if you're right, but this satisfies it. If you plug in X here, let's plug in X. We plug in X here, this whole thing becomes true, right? Because true, X is true. True or anything is true. So this is all true. We're good. All right, here, how can we make this true? Well, Y is false, and not Y then is true, which makes this whole thing true. Now let's look at this last one, the tricky one. We need for either one of these things to be true. So let's take this one first. Is this true? No, because X is T, so that becomes false. Y is F, so this is false, so that's false. But here, Y is false, which makes this true, and Z is also true, so this whole thing is true, which makes this whole thing true, so the whole thing is true. So these are a set of inputs that satisfy this function. Okay? Everybody good with that? Okay. I'm going to tweak it slightly. I'm just going to move an exclamation point. That's all I'm going to do. Now, is this satisfiable? Take a moment. You might be able to guess from my tone.
Yeah, because for the second one to work, you either need Y, in which case half of the first case is fail, or you need for the first case is X and not Z, but that would break.
Right. You can't have not Y, not Z.
Right. You have a contradiction.
Okay. Anybody want to give us some inputs that satisfy this function? Nobody? Nobody has any inputs? Maybe that's a sign. Yeah, because there are no inputs, this is not satisfiable. There are no inputs that make this function output true. And you can actually tell just by looking at it here, in order for this last part to be true, we need either Y to be true or Y to be true. So Y definitely has to be true, but then right here, we have not Y, So these are both going to be false. You can work it out. It turns out to be unsatisfiable. Now, how did you guys go about trying to determine if this is satisfiable? Anybody want to provide what they did?
We brute forced all possible combinations.
Yeah, I heard a lot of, well, let's make X true, and then we'll try making Y true. No, that didn't work. So that's the algorithm, right? You just try stuff. So that's basically what we're going to code, but we're going to do it in a very clever way. So, but first, we need to simplify the problem a little bit. It's very difficult to deal with functions in any form, like you guys just saw. Those functions that I had up on the board that had nested ands and ors, really hard to actually figure out and to reason about. So we're going to introduce a kind of standard form called CNF, conjunctive normal form. If you've taken DLD, you probably know this as product of sums, or an and of ors, or a set of clauses. So let's take our first example here. This happens to be in conjunctive normal form already, because we have an and, that's the first requirement, an and of ors, we have an and. These are clauses here, and the clauses have one variable and no ors. That's okay, we can have no ors. These are the two clauses, and they're separated by an and, so it's conjunctive normal form. Now this example, is this in conjunctive normal form? Raise your hand if you think it is in conjunctive normal form. Raise your hand if it's not in conjunctive normal form. Yep, it's not in CNF. This is not CNF because we have this nesting here. CNF requires an and of ors. So here we have an and of ors, an and of ors, an and of ors of ands. No, not CNF. CNF, we just have two levels, ands and ors. We can't have any nesting. So this is not CNF. But we can put it in CNF. So here's the CNF form of that function. And similarly, this example is not in CNF, but we can put it in CNF. And I'll just state that there's an algorithm that exists that converts from non-CNF to CNF in linear time and space, but I'm not going to talk about it because it's not backtracking. So if you're interested, you can look it up. But for the purposes of this lecture, we're just going to assume that we can transform any problem into a CNF problem easily. Questions about conjunctive normal form? Okay. So satisfiability, how would you solve this? We already kind of saw just brute force, right? You just try stuff. So that's our intuition. We're just going to try stuff. So let's see what kind of code that makes. We've got a function, it takes in an expression, and we're going to try setting some variable to true, just arbitrarily. And then we're going to see if the expression is now satisfiable. If it is, great. Otherwise, we're going to set that variable to false. Now we're going to check if it's satisfiable again. If it is, great. Otherwise, that must not be satisfiable, right? Because we tried setting something and recursing on both possibilities. If neither of them were true, then obviously this isn't satisfiable. Anybody identify a problem with this pseudocode here?
Just one variable.
Just one variable. Okay, so the problem that was identified here is that we're only changing one variable. That's true, but that's actually not a problem because of the recursion here. Every time we recurse, we're going to pick another variable and set it. So over the course of this recursion, we'll end up setting every variable. But there's another problem. Anybody have another problem? I heard somebody whisper it.
Is there no base case?
There's no base case. We're doing recursion without a base case here. So that's definitely wrong. So what's our base case? Well, our base case is that we've assigned every variable, right? We're assigning these variables, and like I said, eventually we'll assign every variable. If we've assigned every variable, then we're done. So that's our base case. There are no free variables. If that's the case, then what we are left with is an expression with only trues and falses, no variables. If we have an expression with just trues and falses, then we can just evaluate it right then and there. And if it's true, it's satisfied. If it's false, it's not satisfied. So we just return that evaluation. And I also left out the step of how we pick that variable. For the purposes of the backtracking algorithm, it doesn't matter. You just pick a variable. But of course, in the real world, it does matter. One thing to note here is that this is very pseudocode. I've completely abstracted away what EXP actually is. And I'm not going to go into that. That's more of a data structures problem. There are data structures that make this operation efficient, but they're more complicated than just sets, and so we're not going to go over them. But just imagine that setting this variable happens very fast, and so we can kind of do it efficiently. Okay? So, you might be able to tell just by looking, this is not an efficient algorithm. And we can tell by writing out the recurrence. This is our recurrence. First off, does the master theorem apply? Raise your hand if it does apply. Raise your hand if it does not apply. It doesn't apply for two reasons. One, because we have this -1 here. But let's say we ignored that -1. What would B be? 1? B would be 1? What's log base 1 of a thing? Yeah, that's not defined. You can't take log base 1. Is my microphone? Yeah. Oh. One moment. Okay, does that work? Am I back on? Okay. So this is not the master method because B is 1. And that means we're taking log base 1 of the thing. That's not defined. And somebody mentioned infinity. Yeah, I mean it's not. It's undefined. But your intuition is right. This grows really poorly. That's exponential. This makes sense because every single time we recurse, we're shrinking the problem by 1, but we're doubling the amount of work we're doing, times 2. So for n, we're going to double 2 to the n. But that's okay, because this works. This is a working algorithm. So let's see it in practice. We've got this expression here, really easy, but let's just execute the algorithm, right? We pick a free variable, and we're just going to pick the first one, x. You set it to true, and we recurse. Now we pick another free variable, we picked y, we set it to true, and we recurse. We pick z, we set it to true. Now we've set all the variables, so we're in the base case, and we evaluate this expression. That evaluates to false, does it not? Got not true and some stuff. Not true and that's what's already false. So this evaluates to false, and so we didn't satisfy the expression. So we pop back up the call stack, and we try setting that last variable that we assigned to false. We're in a base case again, still evaluates to false, so we still didn't satisfy it, so we continue. So you can already see this is a really bad algorithm because we're going to have to recurse all the way down, and then pop all the way back up, set this back to a false, then recurse all the way back down again, just to come up with the answer false, true, true. Right? That's not, we all saw that immediately. So obviously this is not a desirable algorithm. So let's see if we can use backtracking. First off, are we building partial solutions? Yeah, definitely. Because we have this expression data structure, and we're assigning variables as we go. So we're kind of simplifying the problem. We're building an expression that's either satisfied or not. That's a solution that we're building incrementally. Can we determine if a partial solution is invalid? This is the second part of backtracking. If we have an expression with some variables assigned and some variables not assigned, can we determine if that expression is invalid? And the answer is yes. All we have to do is simplify as we go. And if we simplify as we go, it'll be very clear when we make a mistake. And you'll see what I mean in a bit. Note on simplifying here, simplifying becomes very easy in this problem because of conjunctive normal form. So if part of a clause becomes true, remember a clause is a set of OR things. So if one of those things becomes true, then the whole clause becomes true. But if the whole clause is true, then we don't have to consider it anymore, so we can delete that entire clause. What if we only had one clause and we just deleted it? What did we just do? We just solved it. Yep. So if we have an expression with no clauses, we're done. That's pretty nice. Okay, if we have a clause and part of it becomes false, what then? So remember, a clause is a set of ORs. One of those things that's ORed together becomes false. What can we do? We can delete that thing that just became false. Because if we're going to make this clause true, it's not going to be with that part, right? That part is now false, so it doesn't matter anymore. What if our clause only had one part? Let's say our clause was just x. And we just set x to false. Well, then we would eliminate x, right? Because now part of this clause has just become false, so we eliminate that part of the clause. And so now the clause has nothing in it. What does that mean? It means we eliminated everything from a clause. As in, everything in the clause became false. Which means the expression is not satisfiable anymore. We've constrained the expression to a point where one of the clauses was completely false, because we deleted everything in it. So let's see an example. Here we have a function in conjunctive normal form. And let's say we set x and z to true. What does this simplify to? Take a moment, talk to your neighbor, or don't. Anybody? Yeah. Just y. Why is it only y?
Because if x is set to true, then becomes false, you eliminate that part in that clause. And then if z is set to true, just eliminate the clause, and so it doesn't apply.
Yep. Yeah, in that first clause, we set x to true, which makes that first part of that clause false, so we delete it. If we're going to make that first clause true, it's going to be with the y, not the x. So we remove that first part, and the first clause just becomes y. Second clause, we set the z to true. So now we have a part of that clause that's true, so we've satisfied the whole clause. So we delete the whole clause. So this whole thing simplifies down to just y. That's pretty nice. We just cut the problem size down by a significant amount. Any questions about simplification and why backtracking applies? Okay. So our backtracking case is going to be if we make a clause empty, right? That's what we just said is grounds for saying the expression is unsatisfiable. If we set an entire clause to the empty clause, then we removed everything in it, and the expression is no longer satisfiable. So that's our backtracking case. So let's try coding it up. We take in an expression, we still have our base case. But now what we're going to do is we're going to loop through all the clauses. And we're going to say if the clause is empty, return false. That's it. That's the backtracking case. All it is, it's very similar to the base case. It just happens early and returns false if invalid. So that's the backtracking case. We pick a variable, we set the variable, we recurse, but this time we simplify as we go. We simplify, and that'll allow us to identify unsatisfiable solutions by identifying an empty clause. Okay? Questions about this?
So checking if the clause at length equals 0, does that mean there's no parts in the clause?
Yeah. Yeah, so again, this is pseudocode. I haven't said anything about what any of these data structures actually are. But I'm implying here that we can get the size of a clause, and that size is equal to the number of parts in that clause. And so if we check the size is 0, then that's implying that we deleted everything in that clause. Yeah. Good question. Other questions?
So if there's something in the clause that's true, then the clause is just not there anymore.
Yeah, so the question was on simplifying. If part of a clause becomes true, we can delete the whole clause. Yeah, that's true. That's true. Because if part of a clause is true, a clause is just a bunch of ors. So we know that the whole clause became true. And if the whole clause became true, then there's no need to check it anymore. So we just delete it. Yeah. Other questions? Okay. So what's our recurrence? We actually got worse, didn't we? We have the same recurrence, but this time instead of a +1 on the outside constant amount of work, we've got a plus C. We're looping through all the clauses. So we got worse. But asymptotically, that's actually going to be the same, because C is, that C could be an n, could be an n squared, it doesn't matter. The dominating part of this recurrence is the fact that we're only shrinking the size of our problem by 1. So this recurrence is still exponential. So we didn't get any asymptotically better. That being said, you'll see in a second that we got a lot better in the average case. So let's look at this example. Same exact example as before. But now, what do? We pick a free variable, we set it to true. But before we recurse, we simplify this expression. What does this simplify to? Anybody? This right here, what does this simplify to? Yeah, this simplifies to false yz, right? But we said that when we're simplifying these things, if we make a clause false, what do? We remove the part of that clause that was false. So we don't simplify this to a false, we simplify this to an empty clause, right? Not true is false, so we just made this part false, so we remove that part. And we're going to be left with the empty clause, which we detect now. We recurse. We're not in the base case, but we do detect this empty clause. The very first clause has a length 0 now. So we return false, which means we don't set y and z. We just go back to the original. Oh, okay, I put in one fewer animation than I thought I did here. We just go back to the original problem and substitute the true for a false. We backtrack. So now instead of having not true yz, we have not false yz. What does that simplify to? Yz. Yep, because we made an entire clause true, so we delete it. We set y to true, and we simplify. What does that simplify to? Just z. We set z to true. What does that simplify to? The empty expression, no clauses. No clauses evaluates the true. Like we said on the simplification slide, if we have an empty clause, that's unsatisfiable. But if we have an empty expression, if we eliminated every clause, then that means we satisfied the expression. So this is vacuously true. We've found an assignment that satisfies the function. Do you see how backtracking made this much faster? Before, on this exact same example, we didn't even find the solution by the end of the slide, like I ran out of space. Here, because of this simple backtracking early, we were able to find the solution before the end of the slide. Questions about this? Okay. So there's a tradition of including memes in the algorithms lecture, so I had to throw one in. There's a theme in backtracking algorithms. Backtracking is good, right? We backtracked in that last example, and that let us solve the problem before the end of the slide. So we want to backtrack, and we want to do it as early as possible. let's go back to that example. If we had backtracked at the end, like let's say this clause was over here, if we swapped the first and last clauses, then we would have gotten to the end of the expression and then backtracked. And what good is that? We want to backtrack early. So thus the meme. So we're going to try to backtrack early, and the way we're going to do that is we're going to simplify more aggressively by looking for things that we can assign more early. So here's an intuition. If we have a clause that only has one variable, then we have to set that variable to true, or we have to set that clause to true, in order to satisfy the expression, right? So like let's say our clause is a bunch of stuff, x, y, z, and, or, etc., and a. We know right away a has got to be true, right? I mean, whatever the rest of that expression was, if we don't set a to true, the expression is not going to be satisfied. So the idea is we should do that first. At every step, we want to check, have we just made a unit clause? And if we have made a unit clause, set that variable right away. So here's the pseudocode. Same beginning. We still have a base case. Still have a backtracking case. But now, we're going to go through all the clauses. We're going to check to see if the clause length is 1. So before we were checking if the clause was empty. An empty clause is grounds to backtrack. A clause with length 1, that's grounds to unit propagate. So we take that thing, whatever's in that clause, whatever its sign is, set that variable to that sign. So that means, like, let's say we have a full, big long expression, and not a. Well, the sign of that a there is not, false. And so we're going to set a to false. That'll make that last clause true, so we can eliminate it. And we will have just sped up our algorithm by getting to a backtracking case faster. Questions about that for loop? Okay. And then the rest of the algorithm is exactly the same. Okay, so did this make a difference? I don't know. Let's see. Let's take this expression right here. You can probably already tell it's going to make a difference because, look, this is a unit clause, that's a unit clause, and that's a unit clause. We've got 3 unit clauses, so that's pretty sweet. So we're not in the base case, so we loop through the clauses. That first clause, that's a unit clause. Its length is 1. So we get its sign. Its sign is false. So we set x to false. Okay. Now we continue looping through the clauses. We're on the second clause now. That's a unit clause. Its length is 1. Which means we can set y to the sign. The sign is true. So we set y to true. We continue looping. Is this a unit clause? No. Is this a unit clause? Yes, but it has no variables. So I didn't show that in the pseudocode, but if you have a unit clause but there's no variable in the unit clause, then there's nothing to say. Okay, so we've just eliminated all of the unit clauses. So what's going to happen when we simplify this expression? I should have shown more steps in these animations. This would simplify to z empty clause, and then we would assign z to true, because that's the next thing we do. We set z to true, and then we simplify, and then we recurse. So when we recurse now we get our backtracking base case, which means we return. Do you see how we hit backtracking case faster than we would have otherwise? Otherwise, we would have had to assign x, then recurse. Assign y, then recurse. Here we just assigned all of the unit clauses, recursed, and immediately was able to backtrack. So that's pretty nice. So, okay, setting z to true didn't work. Let's set z to false. Does that work? No, because we still have that empty clause. So we backtrack again. Now we're back to the original call to this function. We've tried every possibility. Nothing worked. So this function is unsatisfiable. This is called unit propagation. We look for unit clauses and we set those variables. Any questions about unit propagation?
Could you just explain the clause index 0 part one more time?
Yeah, so what I'm saying here is the clause length is 1. We know that for sure. So we're safe to get the first element of the clause, so to speak. Again, we don't know what these data structures actually are, but we can assume that there's probably some sort of list that's keeping track of all of the parts of this clause. So we're going to get the first part, the only part, because the size is 1. Does that make sense? This is very pseudocode. Yeah.
So just to clarify, are the parts in the clause separated by a union? So if there's one union, are there two elements in the clause?
Do you mean the or here?
Oh, yeah, sorry.
Yeah, so like this clause has 2 parts. Its length is 2. Yeah, good question. I guess I never really specified that, but I'm calling the length of the clause the number of things separated by ors. Other questions?
Why do you check anything else after you get the empty clause? Do you need to?
Yeah, good question here. We know that as soon as we got this empty clause here, there's no need to check z. But I'm just following the pseudocode I wrote religiously. And what I said was, we simplify, assign, recurse. So we don't actually check the empty clause until we recurse, which means we have to assign something first. So it's just a quirk in the order of the things I wrote here. Yeah. Other questions? Okay. Yeah, question?
How do you differentiate empty clause from no clause in Sudoku?
What do you mean by, so the question was how do we differentiate between empty clause and null clause? What do you mean by null clause?
No clause like you have true, true, and true, and then you eliminate all 3 of them, so it's no clause. It's like it's no clause.
True, true, and true?
Yeah.
You said? So that's 3 clauses. And so we would eliminate each of those clauses because they're true. So are you talking about the empty expression, like the expression with no clauses? Yeah, so the way we would identify no clauses, or the empty expression, the expression with no clauses, we would do something like expression.length is 0. That's how we would identify there are no clauses. Because the expression contains clauses. If the length of the expression is 0, then there are no clauses. The way we're identifying the empty clause is we're checking if the clause's length is 0. If the clause's length is 0, then that's an empty clause. Does that make sense? Okay. Yeah, good question. Okay, there's one more optimization we're going to do. Again, we're trying to backtrack as quickly as possible, so I'm introducing simplifications that we can make early to get to the backtracking case fast. So this is the last one. The intuition is that if a variable always has the same sign everywhere in the expression, then we can assign that variable to the sign, to whatever makes it true. And since we can assign that variable to whatever makes it true everywhere, we can eliminate every clause it's in. Okay, let's see the example here. Okay, we've got this expression here. First of all, let's look at x first. X occurs with no not, but then here it occurs with a not, so it doesn't always occur with the same sign. So x is not what we're talking about here. X occurs with 2 different signs. Okay, but let's look at y. Y occurs with a not here, and those are the only 2 times it occurs. So everywhere a y occurs, it occurs with a not. What could we do with that? Anybody have an idea? Yeah, we set y to false. If every time y occurs, it occurs with a not, let's set y to false. Because that's not going to hurt us. You know, if every y occurs with a not, we're not going to hurt the expression by setting it to false. So let's just go ahead and do that. We set y to false here, we set y to false here. What did we just do? We made this clause true, and we made this clause true. And what do we do with true clauses? We delete them. So the implication is here, every time we have a variable that occurs with the same sign everywhere, we can delete every clause that that variable appears in. Okay? So we set y to false here, and that allowed us to delete these first two clauses.
Can you also like do another optimization where if there are unit clauses that are like there's a dot and then there's a not, there's like a without the not, but they're the same variable, you can just say it's not satisfiable.
So the question was, can we do simplifications where we don't have this situation where the variable always occurs with the same sign, but we have the situation where the variable occurs with different signs? The answer is no, because to figure out what the right thing to assign that variable is, we would have to understand the context, the clauses that those variables appear in. Is that, maybe I misunderstood the question.
What if there were unit clauses? Yeah, if both were
unit clauses. So you're saying, what if we have both this situation and unit clauses?
Yeah.
Then we just do both of the simplifications.
But what if they're opposite?
If they're opposite,
Then it's not
they won't be opposite.
I think he's saying if
the
like, you
unit
have the
clauses
unit
are
clause that's
opposite.
y and the unit clause that's not y.
Yeah.
Can't you just like say the whole thing's not satisfied?
That's basically what we're doing. Okay, so the question was, if we have a unit clause that says x, and then another unit clause that says not x, isn't that something we could satisfy, identify early? The answer is yes, and we actually did it on the last slide. On the last slide, we looked for unit clauses. What we would do is find the one with x, and set x to true, and then immediately induce an empty clause somewhere else. And so that's effectively what we're doing by assigning unit clauses. Does that make sense? Okay, yeah, good question. Okay, so here we identified this pure variable y. We eliminated the clauses. There's one more pure variable here, z. Z always occurs without a not. So we're not going to hurt the expression by assigning z to true. If we do that, we can eliminate these two clauses. Okay, so now, without even recursing a single time, we've eliminated every single clause. And what does that evaluate to? True, vacuously. So we've just satisfied this function without doing any recursion. So that's the intuition here. Let's see it in code. Same function as before. We still check for unit clauses. But now we're also going to loop through all the variables and count, identify all these signs that that variable occurs with. And if it only occurs with one sign, then delete all the clauses that that variable occurs in. Again, this is pseudocode. This would not work. But we can understand that there's probably some efficient data structure, and there is, that can do all of this deleting and searching and counting very efficiently. Okay? And then the rest of the code is exactly the same. Recurrence. We still are doing the same recursion. We're still shrinking the problem by the same size, worst case. And now we've gone from C to N on the outside because we're looping through the number of variables. So we're still exponential worst case. But we saw here, in practice, this will allow us to solve problems much faster. So this is an interesting problem where the efficient algorithm to solve it doesn't actually change the asymptotic runtime. The worst case here is actually always going to be exponential. If you've taken theory of computation, then you know satisfiability is NP hard, which means that there are no efficient solutions for it. In fact, satisfiability was the first NP hard problem, just because there aren't any efficient algorithms to solve it doesn't mean we can't solve it pseudo-efficiently. Efficient here means polynomial runtime. We can't solve this problem in polynomial runtime. But we have these backtracking algorithms and these optimizations, simplifications, that allow us to solve the problem in a reasonable amount of time. And that ends up actually being enough to solve satisfiability problems with thousands of variables and thousands of clauses. And this is important because satisfiability crops up everywhere. If anybody here is an ECE and you're doing circuit design, Boolean functions, basically circuits. Or my understanding of them, at least. I'm not ECE, so that's how I think of circuits. And AI, automatic theorem proving, satisfiability crops up everywhere. So this algorithm is really important. Okay, so that was backtracking. Look out for the homework next week. That's going to be due on Thursday on backtracking. It's a lot of fun.
It's hard to say.
Yeah. So, yeah, go to.
She made it. Yeah, what you talking about? KK's? I'm waiting. Undergrad? Go do it. Let's go.